in this video we're going to take a look at a couple ways to graph polynomials, one where we're a little more accurate and one where we're, I guess, a little more sketchy. So in this first video, or this first part of this video, we're going to take a look at the way to be a little more accurate, where I'm actually plotting points. I'm actually going to kind of talk about step 2 first, because I'm not going to pull my calculator up for this video. Our way to be more accurate is going to plot points, and the way I would recommend to do this is to use the table feature on your calculator. So I've already gone ahead and done that. I've made a small table of values down here. There's obviously many more, infinite number of points I could use. If you want to make sure you know how to do that, you may want to pause the video, enter this into your graphing calculator, and make sure you can get the same table of values. Otherwise, you can take my word for it. I've gone ahead and plotted the points, and I want to talk about this whole plotting 5 to 7 points thing. That's just my kind of rule of thumb to make sure I have enough points. You can see that some of these points are going to get really big or really small. I'm not going to be able to include those on my graph unless I use a giant piece of graph paper or adjust my scale. So my rule is to use all the single digits. So I had 4 single digits I could use within that table of values, so I plotted those 4 points. If you want to make a bigger scale and use more points, that's fine if you want to be more accurate. But the reason I wanted to talk about this is if all I did was do this part, I really have no idea what this polynomial looks like. Like, I see 4 points there, and I have no idea what this is. I mean, to me, it kind of looks like the Loch Ness Monster or something. So to be more accurate, what I'm going to do then is, let's go back and talk about step 1, determining the degree and the end behavior of the graph. Well, this polynomial, even though it's not multiplied out, would eventually end up with x to the 3rd power. Not that I'm allowed to distribute exponents, but I know that eventually I'd get x to the 3rd power. So my degree is odd, because it's the degree 3. And then my leading coefficient is going to be positive, because if I were to multiply this all out, the number in front would be positive. So I have an odd positive polynomial, which tells me my end behavior is going to look like this. My graph will start low and end high, which gives me a much better idea of the order to connect these points. And I know I'm going to start somewhere down here, and I'm going to end somewhere up there. So I get a much better idea of what's happening. But finally, I guess to be as accurate as possible, I will want to look at my graphing calculator. So I'm assuming you've already graphed this, or you've paused the video and checked those points, but go ahead and actually look at the actual graph of what the polynomial actually looks like in your standard window, and you can see that, yeah, it matches up to the end behavior we have. We get a really good idea of what it looks like, because sometimes your points won't show you the true nature of the graph. So make sure you're always looking at a graph from your graphing calculator. And then, as my 3rd step says up there, connect these points with a nice smooth curve. I don't know how smooth mine will be on the screen here, but I'll do my best. You want to make sure, oopsie, I kind of missed that point just a little bit. You want to make sure your graph does not have any sharp points in it, because remember, polynomials are like roller coasters. We want to make sure we have nice smooth curves, no sharp points in there. So there's our way to be a little more accurate. I know it didn't really look like it the way I did my graph, but compared to this next example, we're going to see that this is more accurate because we're plotting way more points and being a little more careful. But let's take a look at a way we can be a little more sketchy with how we graph. So just word of warning or word of caution, if I want to graph this the same way I just showed you by plotting points, we certainly could, but I kind of want to approach this from a different angle this time to make a rough sketch. This time, because my polynomial is in factored form, I'm going to be able to plot the x-intercepts pretty easily. So once again, I'm actually going to do step 2 first, I suppose. And I want to find my x-intercepts, or find my zeros. Well, I showed you in a previous video, these are easy to do if they're in factored form, because your x-intercepts are just the zeros. We would set each factor equal to 0. And then solve each part. I mean, most people realize real quickly they can just change the sign. So 0 is a solution, an x-intercept, -3 is an x-intercept, and then 2 is an x-intercept. And then notice what it says. Also note any multiplicities. Those are powers of your factors. And so this -3 has a multiplicity of 2, meaning it counts twice. We talked about in that video with multiplicities, what that means about the graph is that when I get to this x-intercept, my graph is actually going to bounce off the x-axis. It's not going to cross through, because it's got an even multiplicity. My graph is going to bounce. So let's go ahead and get these plotted, then talk about end behavior and see if we can get a good idea of roughly what this graph looks like. So I've got zeros at 0, so I'll put that point on my graph. I've got a 0 and x-intercept at -3, and that's the one that's going to bounce at. So it's either going to come through and bounce off like that, or I mean it could even bounce that way depending on how my end behavior is shaping up. And then I've got a 0 at 2. So I've got those 3 spots where my graph will hit the x-axis. Those are the only points I'm going to plot, because to figure out what my graph looks like roughly, I'm going to take a look at end behavior. This polynomial has a degree of 4. If I were to multiply all of these factors together, I'd end up with a 4th power. I've got 1x there, 2 more of them there for the 2nd power, and then a 4th one there. And then a positive leading coefficient. If I were to multiply this out, my number in front would be positive. A positive even end behavior graph tells me that both ends will point up. So let's kind of put all of these thoughts together to make a really rough sketch of this polynomial. I know both ends of my graph are going to be pointing skyward, so I'll kind of get those, I'll kind of get those drawn in. And then I know my graph is going to bounce at that -3, but pass through those other points. So maybe my graph is going to come down, it's going to bounce off that, it must change directions, it'll pass through this one. It's got to change directions again to get back where it's going to end. So I'm going to say that this kind of W-shaped graph is a really, really rough sketch of what this polynomial will look like based on its zeros, based on the multiplicities, based on its end behavior. If you were to graph this on a calculator, which you can certainly do to get a better idea of what the graph looks like, you'll see that we have the basic overall shape, right? But we're really, really far off as far as how low the graph goes. Like I think it even goes way down lower than -10. So that's why I'm saying it's a rough sketch, but it gives us an idea and it helps us discuss a few things like bouncing and end behavior as a way to get a graph of a polynomial.